Aldridge. There's a couple of things I want to say. Oftentimes when I do a search, I'll do a search based on the formula. And so here I should have written C2O4 rather than OX, most likely. But there are different ways of naming it. They call this potassium chromium 3 oxalate trihydrate. You know. But when they do these, and then they have potassium tris oxalato chromate. I'm sorry? The launcher stuff. Just click no or something. Let me see. Yeah, take it back to your stuff, and then let me see what's going on with yours. You should get a little window. It's probably not crucial. I'll just put it on the screen up here. If you just look at the this. The nomenclature that you see in chemical catalogs, it's kind of difficult, as they don't always follow the same set of rules that we follow. Is it working, Nicole? When you do vision, what does it say? Vision what? Vision? Just click no. I don't know what's wrong with it. You can try to reboot it, but or well, the tricky thing, these chemical catalogs, they don't always use the same names. So I needed to purchase some ammonia. I couldn't find ammonia. Do you know what they called ammonia? They called it nitrogen trihydride. That's what they called ammonia. But it's not really nitrogen. It's closer to hydrogen nitride than it is nitrogen trihydride, because ammonia has an oxidation state of -3 on the nitrogen and +1 on the hydrogens. So it was kind of flipped. But anyway, we have to be careful, because if you see these names online, they aren't necessarily the way that we're supposed to do it. But it looks like they're having a big sale on this. Maybe it's not so useful as it once was, because it was $123 per 5 grams, or maybe they're just making it a lot cheaper now. And so maybe you had about 5-10 grams worth. So it'd be about $50 to $100 worth of the stuff. All right. This is millipore sigma. That's fine. Or Sigma Aldridge. I guess Sigma Aldridge is bought out of a lot of these little companies. So let's go back to our paper. And did we talk about the results section? The results section is, you just summarize the key findings, the factual findings of the experiment. And so after the experimental section comes results. And for ours, what can we say factually? What we can say is that, 9 point, I'm just taking it again, 9.97 grams of blue, green, black, let's say green, black crystals. What color were yours? It's hard to tell. So I'll just say 9.7 grams of black crystals. Obtained. That's all we can say. We don't know, necessarily how pure it is, right? Or even if it's the right stuff. And so the next section is going to be the discussion section. And in the discussion section, we have to talk about what the black crystals are, and what we think. If we have some quantitative data about the purity, that would be great. If we don't, then we'll just have to convince the reader that these black crystals are indeed what we set out to synthesize. If that's the case, then this is going to require the most work. And so the discussion section should be the longest part of your report. Although when you look at the instructions here, it looks like it's very small. 2 paragraphs here. Let's see what they say. When discussing your results, be objective. Point out the features and limitations of the work and interpret and compare your results. Relate your limitations of, Relate your results to your original purpose in undertaking the project. Have you resolved the problem? What exactly have you contributed? Briefly state the logical implications of your results. Suggest further study or applications if warranted. You can present your results and discussion as 2 separate sections, or you can combine them into one section if it is more logical to do so. Conclusion. If you have already presented your conclusion in your discussion section, you do not need a separate section for them. If you do have a separate conclusion section, do not repeat discussion points or include irrelevant material. A conclusion is not a summary. A summary of the paper is the abstract. A conclusion is something new. Your conclusion should be based on the evidence presented. So typically in a conclusion, you suggest further study or applications if warranted. And if that's the case, then your conclusion should be incorporated into your discussion section. And so unless it's a long paper, we don't have a conclusion section. Just the discussion section pretty much ends the bulk of the paper. We don't have a summary. The summary is the what happened to that? Actually, let me download this. This PDF viewer is not great. So we're not going to have a conclusion section. We're not going to have a summary section. Likely, we're not going to have an acknowledgement section. Acknowledgement section is who funded the research. You could acknowledge the state of California or El Camino for providing the budget for this. And the references. References can either be an endnote or footnote style. Special sections or appendices, which we aren't going to have enough data to write a special section. And so our paper is going to pretty much end with references here. We're going to skip some of those other sections. And so for us, it just makes sense to combine the results and discussion section. So we're going to call this results and discussion. The results of the factual observations that you receive, that you obtained in the experiment, you received from the lab, from the experiments. The discussion is your interpretation of what those results mean. And the reason why we keep it separate is because your interpretation might differ from somebody else's interpretation. You know, you might say, well, the chromium-6 was reduced to chromium-3, but somebody else might say, no, the chromium-6 was reduced to chromium-5 or chromium-4, you know. Well, they might have an argument for that. You know, why was it reduced to chromium-4? Why wasn't it reduced to chromium-3? Or maybe somebody else might say it was reduced to chromium-2. How do you know it was chromium-3? Well, yeah, there's certain things we should probably try to investigate, you know. And so the discussion is you're trying to anticipate all these, because when you write a paper in science, the way it works is it undergoes a peer review process. And the peer review process is just to check your work to make sure there's no errors. But then again, you know, somebody may have a totally different interpretation and want stronger arguments. So we try to make sure that whatever we're saying has some supporting evidence for that. And so when we go to chromium, the element, we can look at the common oxidation states for chromium here. The common oxidation states for chromium are +6, +2, and +3. So something like a +4 would be an unusual oxidation state, and +5 as well. This would be fairly unusual. And so upon the reduction, we probably reduced it either to +2 or +3. So what makes us think we reduced it to +3 and not +2? So those are the types of things you think about in the discussion section, because the questions will pop up. The referees are going to start asking questions, you know. What makes you think you oxidize the oxalic acid to, you know, CO2 +4, those types of things? Oh, that might be easier to come up with an argument for. But okay, let's go back to our paper here. And so when we do this, we're trying to we're trying to convince the reader that, you know, our synthetic procedure is what we think it is, and it's sound. And so let's go ahead and start off with the first part of this. Which is the first reaction. So maybe we'll give an overview of it first, although the overview could be in the intro section. In the introduction section, it depends. In the introduction section, you could have just a general overview of the reaction, or the general overview of the synthetic method here, if you want. It could be very brief, or it could be more detailed, but what we don't want to do is we don't want to repeat the same thing here. And so if we had a general overview there, then we're going to provide the details here in the discussion section. And so in the discussion section, we might say the first step in the synthesis was to reduce the chromium-6 to chromium-3. Chromium-6, maybe we'll say in dichromate, chromium-3. And so there are different things we could do. So, for example, we could have a little heading on this, you know. Like reaction 1. If we want reaction 1. And we can get ideas on different formatting and other things as well by looking at other papers. And, you know, some papers we can get full papers. Like one paper I tried to get yesterday. It's taking time to load, but I think it came up here. Yeah. Here the full paper came up. And so let's just take a look. This is the preparation and characterization. Preparations is usually synthesis. The synthesis and characterization of zinc oxide nanoparticle coated paper and its antibacterial activity study. So this is the title, the byline, affiliation, date. Date we probably should include here. Now, is that the date the paper was written or the date the experiment was conducted? Normally this is the date the paper was submitted. And so we might put that in here, submission date. Because normally the experiments go over a long period of time. You see there's a long gap here. The paper was received on April 20th, and it wasn't accepted until August 31st. During that long gap, the referees read the paper. Usually you have like 3 referees. They send this to like 3 experts in the field. And then they read the paper, and then a lot of questions come up. You know, why did you do this? Why are you interpreting it this way? You know, you need to do additional experiments because you don't have enough evidence to support your claim. And so during this period, they might be doing additional experiments because the referees felt that the amount of evidence that they gave was inadequate for supporting whatever conclusion they come up with. And so sometimes this period is very long, sometimes it's very short, depending on how many unanswered questions there are. Obviously, we try to minimize this by answering all the questions before, submitting the paper, and that would expedite things. And then finally, it was published on September 15th, so it just gets in the queue for publication. And then you see the abstract. The abstract, you see the key words here for the abstract. These help in, although zinc oxide should be one of them too. Actually, these aren't necessarily keywords. These are links to whatever. Then the introduction. This introduction section is quite long. They talk about, let's say, the significance of zinc oxide, what it's used for, why it's important. It is well known that the purity of zinc oxide is important for its function. So they talk about the purity of this zinc oxide. And they talk about the preparation method here and some of the other work. Then they get to the experimental. This is the nuts and bolts of this, where they talk about the equipment. For example, a TGA analyzer, thermogravimetric analysis, Perkin-Elmer, the model number. See, they list the chemicals. Yeah, they just bought the nanoparticles. I guess they didn't really make them. This is probably why they called it preparation. They just prepared the samples. All right, now they have the results and discussion. If you take a look at the results and discussion, the results and discussion are by far the longest part of this paper. So they're taking a look at all the results, and then they're coming up with their interpretation of the results. here. And so they have many pages of results and discussion, including this is plausible coding mechanisms, part of the discussion, FTIR characterizations, part of the discussion. All this, antibacterial activity studies, part of the discussion. And this is kind of a long discussion, so they have a separate conclusion here. And here, in the conclusion, what they could do is they could separate, what they should do in the future. But it's not a summary. The abstract is a summary of the entire paper. The conclusion is, where do you take it from here? They have acknowledgments. This is supported by the National Science Council and the university here. And then they have the references. And that's the end of the paper. This is from the Royal Society of Chemistry, which is an English journal. So we can change it. We can get rid of the reaction 1 or whatever. The first step in the synthesis was to reduce chromium 6 and dichromate to chromium 3. And so we can talk about dichromate. But we can talk about that in a little bit. But first, we should talk about the reducing agent. What was used as a reducing agent here? Here, we don't need the amounts. All that stuff is given in the experimental section. But what we should have here is the reaction. And so let's go ahead and write out the reaction here. We had dichromate, Cr2O7, 2 minus. And then we're combining this with oxalic acid, which is H2C2O4. What was the reaction? What was the balanced equation that we wrote earlier? Do you have that in your notes? I have some H pluses that I need in here. I think I need, I forgot how many H pluses. I can add that up.
So, 1 dichromate, 3 oxalic acids, plus 8 H plus. Yields 2, 3 plus 7 water plus 6 CO2.
I'll do the subscripting afterwards. So it depends on the journal, whether you have a space there or no space there. Typically, we have no space between the coefficient and this reagent. We'd have something like this. It also depends on the journal if we write in aqueous. It doesn't hurt to write that in because the convention of not writing aqueous is what I do, but it doesn't necessarily mean that other people do it as well. So I'll go ahead and write aqueous. There's no confusion there.
So here in this reaction, which I just put down, it kind of shows why we say it's chromium 3 plus. How much do we have to explain?
That it depends on what it depends on what the chromium 2, the significance of that. We're probably going to reduce it to chromium 2 or chromium 3. Now, if we go to chromium 3 plus aqueous, we want to know what is the color of chromium 3 in solution, and what is the color of chromium 2 in solution. And so what we could do is we could give certain arguments to head off that question. So, for example, if chromium 3 forms a green solution, we could say that oxalic acid was used as a reducing agent, forming a green chromium 3 solution, and then there's no argument there, And so, is there a color difference between chromium 2 and chromium 3? And so, these are the types of things we look for. And in this. So here, let's try to find some more information about chromium 2 and chromium 3. And so what we do is we kind of just read through this here. We can read about some of the properties. Steely gray, lustrous hard. Chromium metal is valued for its high corrosion resistance and hardness. A major development in steel production was the discovery that steel could be made highly resistant to corrosion and discoloration by adding metallic chromium to form stainless steel. Stainless steel and chrome plated, electroplating with chromium together comprise 85% of commercial use. Chromium is also greatly valued as a metal that is able to be highly polished while resisting tarnishing. Polished chromium reflects around 70% of the visible spectrum and almost 90% of infrared light. So you can almost get a mirror finish, 70% of the visible spectrum. The name of the element is derived from the Greek word, meaning color, because many chromium compounds are intensely colored. Industrial production of chromium proceeds from chromite ore, mostly iron 2 dichromate, or no, that's not dichromate. Dichromate is Cr2O4. Whatever we call that. Ferrochromium. An iron chromium alloy. Oh, this is an alloy. This is not an ionic compound. By means of aluminothermic or silicothermic reactions, etc. In the United States, trivalent chromium, chromium 3 ion, is considered an essential nutrient in humans for insulin, sugar, and lipid metabolism. However, in 2014, the European Food Safety Authority, acting for the European Union, concluded that there was insufficient evidence for chromium to be recognized as essential. While chromium metal and chromium 3 ions are considered non-toxic, hexavalent chromium, chromium 6, is toxic and carcinogenic, according to the European Chemicals Agency. Chromium trioxide that is used in industrial electroplating processes is a substance of very high concern. Abandoned chromium production sites often require environmental cleanup. So it seems like in nature, what is the most common form of chromium? As they're arguing chromium 3 is considered an essential element, so that must mean that chromium 3 must be the most abundant in nature. And so we probably aren't going to get too much of an argument there. But what we might want to do is we might want to see, could it have been reduced to chromium 2? Is that something that's possible? And so we might try to search, this didn't help us, unfortunately, but chromium 2 plus versus chromium 3 plus color. The 2 plus ion is almost the same color as copper, violet, blue, gray color. Okay. What about the 3 plus? The 3 plus ion is green. 2 plus is blue. So could you tell, after the reduction, did you look at the color of the solution? What color was it?
I would say it was
Black. That was after the reduction and before adding the potassium dichromate, right? No, I mean oxalate, right?
Yeah.
Okay.
I didn't hear that it was a hot black.
All right. And it was probably black because the oxalic acid was also acting as a ligand, binding the chromium. So, the reactions were happening at once. And so even though we call that reaction 1, it doesn't go, reaction 1 goes and then reaction 2. Things just happen rapidly in solution. And since we have oxalate present in the form of oxalic acid, it could bind and create our trioxalate chromate complex. But let's take a look at what else we can find here. What else we can find is, why is chromium 2 plus less stable than chromium 3 plus? Well, I kind of figured chromium 2 plus must be less stable because if we find chromium 3 in nature, because it's an essential element, then chromium 2 is likely less stable. Okay, so this is more of a theoretical argument. And so we can say that if chromium 3 is more stable, then that's likely what we formed here in this reduction. So should we write about chromium 2? Well, there are two reasons why we don't necessarily have to write about chromium 2. When we look at the redox chart here, they're going to give the most common. No, this one's not big enough. They're going to give the most common one. So when we look at it here, we see that dichromate is reduced to chromium 3. And so what that means is, just based on experiments, the dichromate gets reduced to chromium 3 rather than gets reduced to chromium 2. And so we don't see another one for chromium 2, although it is a possibility. We're going to say it's an unlikely possibility based on our reduction potentials chart. No, you don't have to reference the chart. The chart is very common. You can just, all the reduction potential charts are going to be the same. All right, so what we can say is that now we can start adding the details. And the details, you can really add in whatever you want here. But what we can say is dichromate is a strong oxidizer. Maybe we'll just say it's a powerful oxidizer because, well, where does it lie on the chart? Let's take a look. It's like chlorine. Would you say chlorine is a powerful oxidizer? What would you rank chlorine as? Strong oxidizer? Powerful oxidizer? Oxygen, oxygen is a namesake for oxidizer, and so we could just say it's a strong oxidizer. Dichromate is a strong oxidizer. And as And this is what we do in the paper. We don't want to do too much self-editing. We're going to edit it later, and so we'll just start talking about dichromate. Dichromate, and as shown in the half reaction below, and as shown in the half reaction below, requires 6 electrons. Let's just write it out, 6 electrons. If it's a number below 10, you're supposed to spell it out. Dichromate. And so here we might as well just, inform the reader of this equation that is dichromate. And since I have it all formatted here, I'll just go ahead and use this. Plus 14H plus 6 electrons. Yields 2 chromium 3 plus 7 H2O liquids. Oxalic acid was used as the reducing agent for 2 main reasons. First, it is expected to be a weak, actually more than 2. We might have more than 2 main reasons here. Maybe we'll just put that, we might modify that. First, it is expected to be a weak reducer with its carbon in the, what's the oxidation state of carbon in oxalic acid? +3 oxidation state. +4, I'll just say carbon's maximum oxidation state is +4. Meaning oxalic acid, each carbon has only 1 electron. To give, to lose. So here, what we can do is maybe we can show, the calculation of oxalic acid's oxidation state. And this takes up space in the paper, and so it may or may not be all that necessary, but what we can say is we could just put in +3 for the oxidation state of carbon. And what's the oxidation state of oxygen? -2. So, and the reason you would maybe put more detail in this particular paper than less detail is because of your target audience. Your target audience is like a Chem, 1A student thing. And so we'll just put in C, H, actually, wait, this is wrong. I need to do one more here, and that is hydrogen. So we'll put it down here. It's going to be H2C2O4. So we can make a little graphic here showing the oxidation state here, and we'll have a figure just showing the oxidation state for this. So we can insert some drawings here. So if I want to make a little thing here, the only thing is if it moves. And so I'm going to add a shape in here. Just going to add an arrow. If you want. I mean, this might be a little goofy. Oxalic acid was used as a reducing agent for two main reasons. First, it is expected to be a weak reducer with its carbon in the +3 oxidation state. Carbon's max oxidation, meaning each carbon in oxalic acid has only one electron to lose. This is important because chromium, because dichromate has chromium in its maximum oxidation state of +6. This high oxidation state of chromium leads to it being being a very strong oxidizer. No, we might as well put in the oxidation states for dichromate in here as well. And so here, when we have an equation like this, we'll call it, we'll start numbering them. So we'll call this one equation 1, or we can call it reaction 1. If I make a figure like this, then I'm going to call this figure 1, the oxidation states. And so, if the target audience were, let's say, regular chemists, then we wouldn't do this. We wouldn't show. Everybody would already know what the oxidation states are. But it doesn't hurt to do it here for us. And so I'm going to control-click my arrow so I can clone it, and then just move it over there. This is going to be +6 minus 2. the weak reducer combined with the strong oxidizer leads to a safer, less reactive redox reaction. However, this reaction still occur vigorously. Actually, I need to make some more stuff in here. So I'm going to probably reformat this quite a lot, but here I'm going to call this one figure 1. And we're going to call this the oxidation state. I'm probably going to add more oxidation states to this. The oxalic acid was completely oxidized to carbon dioxide. And so I'm going to put in equation 2. So what was the half reaction for oxalic acid? Actually, this is not equation 1. That's equation 2. This is equation 1 here. Let me fix that. Equation 1. This is equation 2. My equation 3 is going to be the complete oxidation of oxalic acid. So the complete oxidation was our oxalic acid. Put that in here. Going to CO2 plus H2O. Subscript that. How many H2Os? And what else do I need for this reaction?
Maybe I made a mistake. I don't have any H2O.
Oh, maybe I made a mistake there. It goes to 2 H pluses?
Yeah.
All right, that's fine.
2 CO2.
And 2 CO2s, right? Oh, that's it. And then how many electrons? 2 electrons, right. Each carbon would lose 1. Didn't strike through that. The carbon dioxide effervesced. From the solution, requiring care upon addition of the dichromate to prevent splattering. This is also in the experimental section, but we'll just discuss it a little bit here. And I probably reword this. This doesn't really sound very good. The next reason, well, actually, the next reason that oxalic acid is good is because it leads to a clean product. We don't have to worry about the removal of CO2 because it will just remove itself from solution. And so that is one of the other reasons why oxalic acid is a good reducer. And so we can say that not having to remove the product of oxidation, CO2, is another advantage of using oxalic acid as a reducer, a reducing agent. So I'm going to change this to 3. The final advantage of using oxalic acid is that oxalate is required for reaction 2, the next reaction. Call this equation 3. And what we'll do is chromium 3 is obvious, the oxidation state there, but we'll just add it in here. So we have something like that. Can you think of something else to add to this section? I'll be right back. So, one thing that you could add is what I was talking about earlier about chromium 3 versus chromium 2. Why did it go to the chromium 3? So we can add, let's say, a sentence in here or something of the sort. So chromium 6 is going to be quite reactive. And so what we could do is we could maybe add some word here, like the reactive chromium 6 and dichromate to the relatively stable. It's now when I say relatively, that's very qualitative. We want to be more quantitative. Now, what did they say about the toxicity of chromium 3 in the Wikipedia article? All right, let's go back and take a look at that. What they said about it is this. They said that two things. Trivalent chromium 3 ion is considered an essential nutrient, although there's some dispute about that. And they also said that chromium 3 ions are considered non-toxic. If they're considered non-toxic, do you think they're very reactive? Like they're going to start reacting with a lot of things in your body? No. And so what that means is they have to be relatively stable. In other words, what we can say here is we can go out. This might be pushing it, but to the stable chromium 3 ion. If it's an essential nutrient, then that must imply that they're found in nature. And it's found in nature as chromium 3. The essential nutrient in trace amounts, though. And so this might do. Compared to chromium-2, which have slightly different properties. All right, what was the next reaction here? Yeah. Next reaction, reaction 2 is a formation of trioxylatochromate ions. And so I might say trioxylatochromate three ions were formed by chelating chromium-3 ions. In this case, I'm just going to write it since it's the whole thing. I'll just write chromium-3 plus here. With oxalate from either. It sounds like it started chelating right when we added the oxalic acid because we got the black stuff there. So I'm going to say from both, maybe from both oxalic acid, because it doesn't have the oxalic acid. I have oxalic acid as a reducing agent here, if you look. But was the hydrogen critical for this? In order for oxalic acid to be a reducing agent, take a look at equation 3. What happened to the hydrogen? It's an oxidation state. Did it change at all? No. And therefore, if I use potassium oxalate as a reducing agent, would I have gotten the same result? It does need the H+. That's why I have it in there. But are there, in other words, if we had an external source of H+, would it do the same thing? Yes. And so I could use potassium oxalate, but I'd have to add H+ in the form of maybe HCl or some other acid, right? And so the cleanest would be to add oxalic acid because I need the H+. I think that I said that as a reason, right? We used it in here. But in this particular equation, it doesn't matter because we got the H+ anyway from the oxalic acid. If I use the potassium oxalate, then I'd have to add an external source for the H+ here. But since I already used it, I could talk about that here as well, but I'm not. Reaction 2 was formed from both oxalic acid and potassium oxalate. Both of those have oxalate. And so what we can do is we can write the two different equations here. Now, what I'm going to do in this case is I'm going to insert a drawing. I'm going to try to draw this. So how can I draw this out? Or what I can do is I can try to do it by hand and draw it. But let's see how I'm going to do this here. Probably insert a figure from hand, drawn by hand. So we'll do figure 2. Figure 2 would be the formation of the complex. That is, This is Lewis acid base reaction. And I'll just, obviously you want to draw maybe a decent drawing here, but you probably can do a much better drawing. Actually, let me try. I could also type it in here as well. But then you draw in the oxalate here. And so the first one we could do is just oxalate. So draw by hand. And you want to show this mechanistically because when our Lewis acid attacks, what we want to do is we want to show the lone pairs. Of the Lewis base going to Lewis acid. So I don't have my tablet here, but you can just draw. Okay, so we'll have to give a title to that. And we'll do two. We're going to draw the drawing with oxalate. I did both of these on the board. And we'll do the drawing with oxalic acid. In this Lewis acid base reaction, the chromium 3+ is the Lewis acid, and the oxalate or oxalic acid is the Lewis base. As can be seen in figure 2. So if you draw this out, then you can see it. As can be seen in figure 2, the oxalate is a bidentate ligand. Donating a pair of electrons on an oxygen in each, an oxygen on each carbon to the central metal, forming an octahedral complex. So actually, it's not just one oxalate, it's 3 oxalates. So as can be seen, the 3 oxalates maybe are bidentate ligands, something like this. And then we'll show it here. The oxalates are not monodentate ligands. As the second oxygen can bind forming a five-membered ring. So we can add more to this if we want. But since we're running out of time, let me just add in here, etc. Let's talk about reaction 3, the metathesis reaction. Precipitation of K3 sky. Last solvent exchange. Potassium salts in general are highly soluble. One method to reduce the solubility is to use a less polar solvent. A less polar solvent than water. One method to reduce solubility is to use a less polar solvent than water, like ethanol. The transition from water solvent to ethanol as the solvent is easily accomplished because ethanol and water are miscible in one another. By increasing the proportion of ethanol in the mixture, this solubility this salt should decrease, allowing the ions to precipitate to combine, allowing the items to combine in a metathesis reaction, resulting in a precipitate. All right, I'm over time, so I'll stop here. All right, and then we'll just continue this as we go along. So we have the bulk of the paper here. I'm just going to fill in some more details. That's it. Okay, so I'll stop now, and then we'll take another look at the paper next week. Okay, any questions? Did somebody come? You can print out the paper if you want. Printer.
Thank you.
Okay, thanks. See you tomorrow.